Okay, so now that we've talked about inductors, we want to put them in a circuit. It's called an RL circuit, resistor and an inductor. To do this, we're going to make a big comparison with an RC circuit that you already know. So an RL circuit is going to have a source of EMF, a switch, an inductor, nice pretty coil, and a resistor, nice and pointy. An RC circuit, remember, would be almost the same. Battery, switch, capacitor, and resistor. So R and C, same EMF. Now I want to remind you what happened in a circuit like this when you close the switch. The capacitor is uncharged, so it can handle a lot of charge. It wants to be charged if it's connected to a source of EMF. So electrons leave here and go, woohoo, we can fill this up, and they repel electrons up here and they go back to the battery, and electrons, so we end up having electrons pushed overall to this side. We get a negative charge and a positive charge on here. So the charge doesn't happen immediately. It grows over time. So the charge over time, remember we eventually came up with the equation, the final charge times 1 minus e to the negative t over tau. Now two things about this. Remember, charge on a capacitor is given by C times V, and tau is the time constant. And for a resistor capacitor circuit, it's R times C. And we call it the time constant because that's how its units work out. An ohm times a farad equals a second. Now, it also has to work out, because if we want to raise anything to a power, we have to raise it to a pure number. You can't raise any base, like you can't raise 2 to 5 meters. You can raise 2 to the 5th power, but because you're multiplying by itself, there can't be a unit in here. So if we've got time divided by something, this also has to have units of time, and it does. The role of the time constant is it tells us how quickly this charges. The bigger the time constant, the more time it takes to charge this capacitor. Now, the other thing we got from this was current flow. Lots of electrons want to go to this empty capacitor, but then as the capacitor fills up, they don't have as much reason to go. There's a buildup of EMF over here is one way to think about it. And so if like this is 10 volts, well, now that this has 2 volts, there's only an 8 volt potential difference to drive current. And then more charge, greater potential across this, maybe it's up to 5 volts, so less and less. So we start out with a lot of current from charges trying to get over here and fill this up to less and less current. And the equation for that, let me see, make sure I stay on the screen. I of t equals the initial value of current times e to the negative t over that same time constant. So this same term, but instead of 1 minus, it's regular exponential decay. So the charge went up to some final value, the current goes down, both with the same e to the negative t over tau term. Please remember that current is given by EMF over resistance. Now we're going to go to an RL circuit. So when we first close this switch, we have a coil. Coils, if you have a coil of wire, all wires make magnetic fields, but a coil of wire says, don't change my magnetic field. So when you close this, so you have no current, and now you're eventually going to have current based on I equals E over R, the inductor says, no, I don't want that stinking current. And so it makes a back EMF to prevent that current flow. And at first it makes one equal to the battery, so there's no potential difference between these two. There is no current flow. But then it gradually starts to lose, and eventually we do have full current flow given by this equation. So no current rising to maximum current, just like charge on a capacitor. So our equation for the current over time on an inductor is you're building up to a final value. So it's the final 1 minus e to the negative t over tau. So there's a time constant again, but it's a different time constant. This time the time constant is the inductance divided by the resistance. So instead of capacitance time resistance, it's inductance divided by resistance. Now you should check on your own that the units work out. So the inductance is a Henry, the resistance is an ohm, and yes, this is equal to a second. This is another way of that this is a time constant. So again, before we do the next part, a capacitor wants to fill up, but it takes a while to do so. And There's a lot of current charge moving, so there's lots of current, and then there's less and less and less current, and eventually there's no current. So when you first start to charge a capacitor, it acts like a bare wire in a circuit. When it's finished charging, it acts as a break in the circuit. An inductor is exactly the opposite. When you first close the switch, this says, no, I have zero current, I still want to keep zero current, so it acts like a break in the circuit, no current flow. But it eventually loses, and then it's a bare wire. So the current builds up to some maximum value. And it's a bare wire because if this is an ideal inductor, all it is wire coiled. So it doesn't have any resistance. So it is a bare wire once you eventually get enough current, or once you've reached the maximum value of the current. When the current is no longer changing, you've reached your maximum value, it just says, okay, fine, keep going. Now, if we wanted to find the potential difference split here, you know these two always have to add up to this. That's the loop rule. Well, to get the potential across the capacitor, you do the Q expression divided by C. To get the potential across the resistor, you do R times I, using this one. So to do the same thing here, to get the potential across the inductor, we've got to use that equation. Remember that the potential across an inductor is negative L di dt, which means we need to take the derivative of this to get this EMF across the inductor as a function of time. I added those because one, a function of time, but also this is the inductor versus the plane E is for the battery. So we got to do a derivative. Negative L, and then the derivative of this expression. Now this is a coefficient, so we keep it, IF. Then we do the derivative of the parentheses. The derivative of 1 is a constant, so that's 0, minus the derivative of this puppy. So the derivative of an exponential, I mentioned this before for you non-calculus people, is itself divided by the derivative of the top. So the top is negative t, our variable, divided by tau, a constant. So our derivative is just negative 1 over tau. So we actually have 1, 2, 3 negative signs here. So we end up with a negative. We have our L. We have IF. We have tau in our denominator. And then we have e to the negative t over tau. So that looks kind of messy, and we know tau is L over R. So negative L over R. We also know the final current is given by the battery. So EMF of the battery divided by the resistor. So this is EMF of the battery divided by the resistor, e to the negative t over tau. Well, we have an L over R and we have an L over R. They cancel. So the EMF across the inductor is the negative EMF of the battery times e to the negative t over tau. There is a back EMF. So, and the negative sign, as you know, there's a gain in the battery, there's a loss over the inductor. That makes sense. So magnitude-wise, if you wanted to find the magnitude of the EMF across the resistor, you would do I times R. So this expression times resistance. Well, that would then be the whole I times R, which is the EMF of the battery, minus this term. Well, that means it's going to be the same thing as these two always have to add up to this. So whichever way you calculate it, if you calculate one of these, if you get the resistance, the EMF across the resistor from the I times R, and then you want it across the inductor, you could just do battery minus this, gives you this potential. Or you can do it from this exponential equation. You get the same expression. So now we're going to need to do one more thing with this inductor. So back to the inductor. I will redraw it. We always draw switches open, but this switch has now been closed for a really long time. So R and L and switch and EMF. So if the switch is closed a long time, we've reached a steady current equal to EMF over R. When we open the switch, the current's going to die off. We know we can't have current flow anymore because it's no longer a circuit. That makes the inductor mad, of course. It wants to keep current because it doesn't want its magnetic field to change. So when you open the switch, L keeps the current going. but it does so while losing. So you start from a high value and go down to 0. I hope that sounds familiar. It's even still on the screen. There's the current dying off in a RC circuit. So after you open this switch, the current doesn't fall to 0 immediately. It falls to 0 according to this equation. So I of t equals initial current e to the negative t over tau with the same time constant. So a lot of very similar things for RL circuits. Now the last thing I'll say, and I'll slide this back up, I will remind you that we got this equation by solving a differential equation that we set up using Kirchhoff's loop rule. And we did a lot of calculus to get this equation. You can do the same thing to get these. But it's a really useful technique to notice when things work together. It's the same behavior, so we don't have to redo all that calculus. But if you want to check, you can see that setting up the loop rule here with the EMF across the battery and then the inductor and the resistor, so you'd gain, and then 2 losses. You're going to get the derivative of I, and this is directly with I, and you solve the equation, and you get this exact same thing. If you'd like to see that, it is in your textbook, and I'm sure you can find a YouTube video for it.